So students, they repeat this Laplace and Poissons equation. You in the previous video was not clear. That's why I am doing this video again. So Laplace and Poissons equation are very important from examination point of view, since 10 marks question always comes in exam particular topic. Now Laplace and Poissons equation. First of all, what is the need of Laplace and Poissons equation? Now, generally, we have calculated how to find field intensity, line charge, and sheet charge or surface charge. Where for line charge, we are having continuous distribution of the charge of the region. Or by the second way, electric field intensity can be calculated by E is equal to minus of del V when potential V is given throughout the surface. But there are certain regions where the charge distribution is not there, neither nor the potential is there. So the charge will reside on boundaries. Such type of problems known as static boundary problem, and the electric field due to these charge can be calculated by the method of Laplace and Poissons equation. So this type of problems, field and the potential are by using equation, Laplace equation. Laplace equation is one of the form of this equation. Now, first we will go through the derivation of Laplace and Poissons equation, always asked in the examination, and then we will see the numeric based on Laplace and Poissons equation. Now, for derivation, we all know that del dot D is equal to rho V. This is the point form of Gauss law, which we have already discussed. Del dot D is equals to rho V. But also know that D is nothing but epsilon E. So we can write del dot epsilon is equal to rho V. Now, from homogeneous medium for which epsilon is constant, we can write del dot E is equals to rho V upon epsilon. Okay, this point I think it is clear, since rho is constant, epsilon is constant, so we have taken it down. Also, we can write is equal to minus of del V. So put del dot, instead we have to put minus del V. Del dot minus of del V is equal to rho V upon epsilon. Taking minus sign on right hand side, we get del dot del V is equal to minus rho V upon epsilon. Or we can write it as del square V is equal to minus rho V upon epsilon. So del square V is equal to minus rho V upon epsilon is Poissons equation. This particular equation is known as Poissons equation. Okay. Now, in many boundary problems, the charge distribution involved on the surface of the conductor, for which volume charge density is equal to 0, or we can say that rho V is equal to 0. When the rho V is equal to 0, the equation will convert into del square V is equal to 0. This particular equation is known as Laplace equation. Students, we have the Poissons equation, which is del square V is equal to minus rho V upon epsilon, Poissons equation, and del square V is equal to 0, Laplace equation. Now, these are the formulas of Laplace equation in the three coordinate systems. We all know that del V is del V upon del X of V X plus del V upon del Y of Y A Y plus del V upon del Z of AZ. And del A is del upon del X of AX plus del upon del Y of AY plus del upon del Z of AZ. Now what is del square V? Del square V is nothing but it will be the dot product of these two. So it will be ax dot ax will become 1, ay dot ay will become 1, and az dot az will become 1. So we can write it as del square v upon del x square plus del square v upon del y square plus del square v upon del z square is equal to 0. This is the formula for Cartesian system only because coordinates are in x, y and z. So this is the formula for Cartesian system. In cylindrical coordinates, del dot v is del upon del rho of v a rho plus 1 by rho del upon del phi of v a phi plus del upon del z of v z. This is del dot v. Similarly, del dot a is 1 upon a of rho del by del rho of rho a rho 1 by rho del by del phi of a phi is del by del z of az. So again, when you make the dot product of these two, you will get 1 upon rho del by del rho of rho del v by del rho plus 1 upon rho square del by del phi of v plus del upon del square v upon del z square is equal to 0. So learn this formula. It is for cylindrical system. For spherical system, del dot v is del v upon del r of ar plus 1 by r del v upon del theta of a theta plus 1 by r sin theta del v upon del phi of a phi, and del dot a is 1 upon r square del by del r of r square a r 1 by r sin theta del by del theta of a theta sin theta plus 1 by r sin theta del by del phi of a phi. And del square v is del dot v. But it is v. Its Laplace equation will become 1 by r square del by del r of r square del v upon del r plus 1 upon r sin theta del by del theta of sin theta into del v by del theta plus 1 by r square sin theta del by del phi of v by del theta. Learn these formula. This is for r, this is for theta, this is for phi. So you have to learn del square v for Cartesian system, for cylindrical system, and for spherical system. Now, what type of question asked in the examination? Using Laplace or Poissons equation, we can obtain potential at point between two surfaces when potential at two surfaces are given. So, there is a boundary condition given, or it is given that these are the potential of between the two surfaces and out the electric field. You have to use this formula. We can also obtain capacitance between these two surfaces. So in numeric, they will not mention by using Laplace and Poissons equation. What they will do, they will give you the boundary condition, or they can give the potential between the surfaces and ask find out E, find out B, find out the capacitance. These are the general problems which can be asked. Now consider this example. Two parallel conducting discs separated by distance of 5 mm, z is equal to 0, z is equal to 5 mm. V is equal to 0 at z is equal to 0 and V is equal to 100 at z is equal to 5 mm. Find the charge densities on the disk. Charge density on the disk, that means you have to calculate charge density D. Now D can be calculated by using E. E can be calculated by using Laplace and Poissons equation. Now in this question, they have given this. That means this is the problem of cylindrical coordinates. Instead of this mentioned plates, then it will be a problem of Cartesian system. Since mention here discs, it will be a problem of cylinder. So assume one cylinder in which distance between the discs is 5 mm and the potential is V is equal to 0 when Z is 0. So at the bottom surface, we are having z is equal to 0 with v is equal to 0 and z is equal to 5 mm. The value of potential is 100. So here the z coordinate comes into picture. So we can say that the equation which is del square v is del square v upon del z square is equal to 0. Since when you see the potential in spherical, square v upon square v upon del y square, we are not having these values. So we can say that del square v is nothing but it is del square v upon del z square. So v upon del z is equals to a. Once you integrate it and when you again integrate it, this will become v is equal to az plus b. Now putting the values of initial condition, we have to find the values of a and b. So when you put b is equal to 0, z is equal to 0. This is value in equation number 1. B is equal to 0, z is equal to 0. You will get the value of b which is equal to 0. B is equal to 0. And then put v is equal to 100, z is equal to 5 mm. So it will be 100 is equal to a into 5 into 10 raised to the power of minus 3 b. The value of b was 0. So from here we can calculate the value of a, which comes out into 10 raised to the power of 3. Putting this value in equation, the potential is that. So here we can get v is equal to 20 into 10 raised to the power of 3 into z. So hence we can find out the value of z. Now v can be calculated as minus of del v. By using the formula we can calculate minus of del rho of a rho plus del v upon rho del phi f a phi plus del v upon del z of a z. Since you know v, you can calculate e also. So e is minus del v upon del z of a z. So it is minus of 20 into 10 raised to the power of 3 a z. Here you can see that the medium between the disk has free space which gives the flux density. You have to calculate d. So we know that d is nothing. D is epsilon 0 e. So it will be 10 raised to the power of minus 9 upon 36 pi into minus 20 into 10 raised to the power of 3 az. You will get d is minus 0.177 into 10 raised to the power of minus 6 az. This is the complete flux density. So d is constant between the phase and normal to the phase. So that we have to calculate surface charge density, write it as dn, which can be written as plus minus 0.177 into 10 raised to the power of minus 6 az per meter square. This is the surface charge density which is asked in the examination. Question. Friends, you have seen that problem which you have discussed. First, we have to find out v using Laplace and Poissons equation. Then we have to calculate e by using e is equal to minus of del v. Then you have to find out d, which is epsilon naught e, and then you have to find this. Most important which you have to do in this numerical is you should know the formula of del square v in cylindrical, Cartesian and spherical coordinates. Okay. Now the remaining numerical we will see in the next tutorial. Only practice. Thank you.